All right. So in the last section, or the first section of this lecture, we spent some time um, getting comfortable with, or coming into familiarity with, this idea of simple ligand binding and talking about oxygen binding by the globins, right? And I ended that section of the lecture talking about the interaction between protons and oxygen binding to hemoglobin, and the fact that these binding events are not independent of each other. They're linked, specifically, they're thermodynamically linked to each other, right? And they influence each other in important ways that are very directly related to the physiology of oxygen transport, excuse me, in organisms like us. All right, so what is that idea of linkage in the case of binding, um, ligand binding, or binding functions mean, right? We talked about it, thermodynamic linkage, in the context of the cooperativity of protein folding. And it's the same basic idea here, but now we're talking about binding of two ligands that can come on and off a macromolecule, and those being thermodynamically linked. Well, to understand that, we first have to be able to quantify ligand binding, right? We need to be able to describe ligand binding in a mathematically rigorous way that lets us make some predictions about how that binding is influenced by thermodynamics and other parameters of the system, right? So in order to do that, there's some things we need to know, right? So let's say we wanted to come up with a way to characterize and quantify binding of hemoglobin, oxygen to hemoglobin, right? So ultimately, this is the system we're going to be talking about as our example, right? All right. And what we want to know is, how do we describe that in uh, a quantitatively useful way? All right, well, there's some things we need to know, and then some things we need to do for that to happen. The first thing we need, right, is we need an assay, right? Because ultimately, we're not just doing this theoretically. We want to measure something, right? So we need an assay, a method of some kind, right, that lets us measure either the concentration of the complex, right? In this case, that would be the hemoglobin oxygen complex, or the concentration of the free ligand, right? The unbound ligand. That's another way to do this, right? So that would, in principle, be like the unbound hemoglobin would be another way to do it, right? Okay. Turns out there are lots of ways, especially in modern era, in which you can look at formation of complexes, or the amount of the free ligand left over, all kinds of different techniques. But in the case of hemoglobin binding by oxygen, there's a really simple one, right? And it has everything to do with what we were talking about a few lectures ago, and that's spectroscopy. Turns out, you guys remember, hopefully, that arterial, oxygen saturated blood, and venous, or oxygen depleted blood, have different colors. And they have different colors because binding of oxygen to that octahedrally, that remaining position, right? And that position above the heme, between that one histidine and the remaining ligand position of the iron in the porphyrin, binding of oxygen changes the electronic structure of that system, right? So that conjugated ring system, that is the porphyrin, which absorbs light beautifully, right? When there's no oxygen around, deoxymyoglobin has a transition state dipole distribution centered here around an absorption of around 545, 550 nanometers. That looks like a nice classically broad absorption spectrum, as we talked about a couple of lectures ago. But when oxygen binds, you get a change, right? And you get this separation. You essentially get a second transition state dipole over here, right? That changes the color. So the frequency of light that's absorbed shifts, right? And the light here at about 560 nanometers now is not as well absorbed. There's light over here at 540 or at 580 that's now much more better absorbed. And consequently, the color spectrum of oxygenated blood changes. And so it's trivial now to sit here, say at one of these wavelengths, and monitor the binding of a solution of hemoglobin to oxygen, right? Okay, that's great. So that's one of the first things you got to know. So in the case of hemoglobin and oxygen, this turns out to be pretty simple. So we're good on that front. Second thing you got to know is some things you want to measure. And in the case of ligand binding like this, simple ligand binding, there are at least usually a couple of initial things you want to measure, right? The first is you want to know the number of ligands bound per protein molecule, right? And that usually gets a symbol, and it's typically given the symbol N, right? The other thing you usually need to measure, you want to measure, is the equilibrium constant for this reaction. So we know there's an equilibrium constant here, right? So you want to measure that, right? And specifically, the form of the equilibrium constant we're going to use is the so-called dissociation constant. Also given the symbol, typically given the symbol K sub D, right? Now, why the dissociation constant? I'll explain here in a moment, right? Okay, so we got to have an assay so we can do the experiment, measure the binding somehow. We need to have some idea of what we want to measure. And generally the things we're after in a binding experiment are the amount of ligand bound. This is also sometimes known as the stoichiometry of binding. Let's go ahead and note that here. Right? And then the binding constant, right? Okay, or the dissociation constant. The third thing we need in order to describe ligand binding is we need a model, right? We got to have a model for the binding, right? And specifically, we want a model, as I started out this course by describing, we want a model that is quantitative, not just descriptive. And the reason we want a quantitative model is we want to be able to measure the value of those parameters, the stoichiometry and the dissociation constant, right? All right. Okay, so what would this look like? All right. So let's use the simplest possible case we can come up with, right? And that would be something that looks like this. Simple single site binding. Okay. Okay, so some definitions here. Let's just abstract this a little bit. It's a little easier to write down than HB and whatever. Let's say, let's let P, symbol P, equal our protein. And we'll let L equal our ligand, right? And our simple binding description would be simply P plus A. P binds to A to give the complex PA. And we have associated with this then that equilibrium constant, dissociation constant, right? And I keep calling this a dissociation constant rather than the equilibrium constant. It's an equilibrium constant, but it's formed in the opposite manner from the equilibrium constants we've been talking about up to this point. The dissociation constant, remember the equilibrium constant was the ratio of the products of the reactants. The dissociation constant is the inverse, right? The KD is defined as the concentration of the products, concentration of the reactants, P times concentration P times concentration of A, divided by concentration of the complex, right? Okay. Now, so here's a question. Why? I mean, why use the dissociation? Why flip it around, right? Okay. Well, this is one of the situations where it's useful as long as you're not taking this number, right, and pumping it into a mathematical operator like a logarithm that requires it to be unitless, and therefore you don't have to think about activities strictly. Keeping that concept of the concentrations around becomes really useful, right? So if we leave those concentration numbers in place, look at what happens if you think about the units of that expression, right? What would they be? It'd be like, okay, so I'd have molar maybe times molar divided by molar. So molar squared divided by molar is molar. That's cool. If you flip it around, if you use the association constant, what is the, and that's sometimes given a K large A, the units of the association constant would be molar to the -1. Would you rather think in molar or inverse molar? It's harder to think in like, inverse molar. What exactly does that mean? But if you think about the dissociation constant and you think about the fact that it's in units of molar, the dissociation constant, as it gets smaller, as this number, this KD number here, as that gets smaller, that has to mean that the concentration of the product of the reactants is getting lower and lower and lower and lower and lower relative to the concentration of the product. Okay. That means you're making more complex. As the KD gets small, you're making more complex, which means the smaller the number, smaller the dissociation constant, the operationally, the tighter the complex, the easier it is to make that complex, right? At lower concentrations, right? Okay, so that's the reason that biochemists love to use and will prefer to use the dissociation constant when they're talking about phenomena like this. All right, so with this expression for the dissociation constant, and this as our model for the binding phenomena we're looking at, there's one more thing we need. Right? We need to define another expression that's known as the degree of binding. We're going to define something called the degree of binding, right? It gets the symbol nu, right? And it's essentially, it's a simple idea. It's simply the moles of our ligand, so the moles of A bound, right? Per total moles of P, right? So mathematically, what that would look like would be something like this. The moles of P bound is equivalent to the concentration of our PA complex divided by the total amount of P, which is a combination of the amount of P that has no ligand bound, plus the amount of P that's bound, right? Okay, that's pretty simple. All right, so that's what we want to end up measuring, but for this to be useful, we need to figure out a way to put these two ideas together. We need to link them up somehow so that when we measure, in principle, the degree of binding, we can extract from that measurement the dissociation constant and the stoichiometry. All right, well, that's pretty straightforward because what we can do is we can rearrange this expression, right, mathematically. All right, so let's rewrite that KD. We're going to solve it for the concentration of the complex, right? So we rewrite that expression. It's going to look a little bit like this. Concentration of the complex now simply equals concentration of P times concentration of A divided by dissociation constant. Okay. That's cool, because now I can take that term and I can substitute it in here, here, and here to write this expression in another way that's really useful, which looks something like this. So that means if I substitute that definition that includes the dissociation constant for the ligand complex, my degree of binding expression will just turn into this: concentration of P, concentration of A, divided by the dissociation constant, divided by concentration of P, plus concentration of P, concentration of A, divided by the KD. Yeah, okay, cool. Well, that's nice, because now that cancels, that cancels, that cancels. I can multiply through with my KDs, right? Which means the degree of binding is simply equal to the concentration of A divided by the KD plus the concentration of A. That's really cool. I want to write that again down here for you. So go through that little simple derivation. The degree of binding is simply equal to the concentration of A, right, divided by dissociation constant plus the concentration of A. Now, formally, technically, one would have to keep track of the concentration of A that's bound versus the concentration of A that's free. You normally do these experiments under conditions where the constant amount of A that gets bound is relatively small compared to the total amount of A. So this A in this I haven't been explicit about it, because depending on how you do the experiment, you got to be careful. But in general, it's a reasonable approximation that if you do the experiment the right way, the concentration of A here that we're looking at is essentially the total concentration of A sort of in the experiment, right? Now if you do this under certain conditions where the amount of bound ligand is a large fraction of the total, this relationship is going to break down. You got to modify it. But when that's not true, it's a pretty good approximation to just simply use the total amount of A present if it's a relatively small fraction of the total that gets bound, right? And that's usually how you do experiments like this, but just something to be aware of. Okay, so that's the expression we need. Now the question is, what do we do with it? How do we use that, right? All right, the answer to that is we have to do an experiment. And provided we can measure this, right? And provided we know that in our experiment, we can take that data. We've got our model here now. We've solved that problem, right? Here's our model. And we can use that to do a little nonlinear fitting or a little graphical analysis, and we can go after these numbers that we want, right? And we'll do that in the next part.